Okay, so far we have two types of notation. We have 2 to the power of n, and we have n choose k. Now these notations are actually somewhat related to each other. So far we've used this notation to count how many total subsets there are in a set, and we've used this notation so far to count how many total subsets of a specific size, or how many subsets have a certain amount of elements in a set, from a set. But is it possible to look at these the same way? And the answer is yes. In fact, this is actually a better way of looking at n choose k. Let's take, for example, the set that's easiest, and that's going to be the set A, where A contains the elements 1, 2, and 3. We know that the total number of subsets that A has is going to be 2 to the power of 3, which is going to be 8. Okay, but what else can we notice here? Let me quickly write out all 8 of these subsets so you can better see how these work together. Here are all 8 of our sets, and we know we can compute this using our equation up there, where n is going to be 3 because A has a total of 3 elements. But you know how else you can look at this problem is, okay, I have 3 elements of A. That means when I'm looking to choose elements, I can choose 0 elements here, I can choose none of them, right? I can choose 1 element here, I can choose 1, 2, or 3. I can choose 2 elements out of here, I can choose 1 and 2, 1 and 3, 2 and 3. Or I can choose all of the elements when I'm looking to pick some elements out of this set. Well, what does this correspond to? Well, that means when we look at all 8 of these sets, when we say we can choose 0 of them, actually, let me write this out in the notation. So what did I just say? We can have the following options. We can have 3 choose 0. We can choose out of the 3, we can choose none of them. Out of the 3, we can choose 1. Out of the 3, we can choose 2. And out of the 3, we can choose 3. So how does this translate? Well, if we look at all of the possible sets, well, it's true. Out of the 3, we can choose none of them. That's what this option over here is. Next, we ask, well, what if we just choose 1 of the elements here? Well, 3 choose 1. That's going to be asking, well, that's going to be all of these sets, right? These are when you just choose 1 of the elements here. Okay, fantastic. Let me get a different color. Okay. What if we want to choose 2? We want to pick 2 elements out of A. Well, that's going to be these over here in purple. And then if we want to choose all of them, there's usually only one way of doing that, and that's going to be this. I'll circle this one in black. This set down here. So all of these options that you can possibly pick out of your A are going to be equivalent to here. It's going to be equivalent to choosing none of them, 1 of them, 2 of them, or 3 of them. You cannot choose 3 choose 4 because there's not 4 elements in A. You can't choose a negative number because that doesn't make any sense. So what do we notice here? Well, if we count how many options, remember, the choice at the end of the day is how many possible combinations or possible ways can you choose 0? How many possible ways can you choose 1? Well, let's look at this. How many possible ways can we choose none of the elements? The answer is 1. There's only one way you can possibly look at this and say, okay, I want to choose none of them. That's one option. That's 1. That's this option over here. There's only 1 circled in blue. Okay. How many ways, 3 choose 1, can I choose 1 element? Well, let's count them. 1, 2, 3. There are 3 ways to choose 1 element out of our 3 choices. Fantastic. How many ways can we choose 2 elements out of our 3 possible? Well, that's going to be 3 different ways, right? Okay, and finally, how many ways can we choose all of them? And the answer is, well, there's only 1 way. And what do we notice? These are all the ways you can choose something, all the ways you can pick something out of A. If you add all of these up, you will get 1 plus 3 is 4, plus 3 is 7, plus 1 is, in fact, 8. So what did we just find? We found the exact same answer we did with our top formula using our choose logic. So basically, this is equivalent to saying, okay, what if I choose none? What if I choose 1? What if I choose 2, 3, so on and so forth until you get to your maximum number of elements? That is what we're asking. We're adding up all the possible ways of choosing none of them, all of the possible ways of choosing 1, all of the possible ways of choosing 2, all of the possible ways of choosing 3. Add them together, it's the same as saying 2 to the power of 3 is in fact equal to 8. And one more note I want to make. I know when I was saying, well, how many ways can you choose 1 out of 3? I counted them up here. You can just compute 3 choose 1. 3 choose 1 is going to be equal to 3. Oh, this marker I think is dead. Yes. Okay. Let me get this one. So if we want to say 3 choose 1, that's going to be the same as saying 3 factorial over 1 factorial times 3 minus 1 all factorial, which is going to be 3 times 2 times 1 over 1 times 2 times 1, because 3 minus 1 is 2, and then 2 factorial is 2 times 1. The 1 and the 2's cancel up top, and we get 3, which is exactly the number we got here. You can do the exact same thing with all of these and get these numbers down here. So that is how 2 to the power of n is in fact connected to n choose k. And we're going to see how we can use this later in our next set of problems.